Thank you all for coming.
Hey,
Are we?
yes, we are.
Yeah, great.
Great.
And we are on Zoom too, right?
That's okay.
Yeah. So it's my pleasure to introduce Tobias Kipenberg. He's a very distinguished and accomplished researcher, pioneer, arguably the pioneer in the field of cavity optomechanics and Kerr combs, as well as a number of other things. He did his habilitation in Munich, his PhD at Caltech, PhD and postdoc at Caltech. And I think I met you in 2005 when you were interviewing at MIT. I was still in grad school. I was blown away by what you're doing, and you still continue to blow us away with a lot of, really a consistent level of innovation in your research. So it's really a pleasure to have you here. Tobias actually received one of YQI's awards just a couple of years ago. And there's a long list of awards that Tobias has received, well deserved. And so let's hear what Tobias has to say today about frequency combs.
Okay, thank you, Peter. First of all, it's a real pleasure to be here, and also, as you said, coming here another 5 years. I see the tremendous excitement and things that are happening in the field of superconducting qubits, and it's really, remarkable kind of see the how things have progressed. What I choose to talk today about is a topic I'm very passionate about these days, and it's really like to tell you about kind of, if you want kind of a new field of integrated nonlinear photonics, and I like to tell you about chip scale frequency combs. So our effort that's really long lasting now, almost 15 years, to make chip scale optical frequency combs. But then I also touch base to more modern development, actually my group, where we leverage integrated photonics to make cryogenic interconnects. And I think that also connects some of the work, of course, down here. Before I forget it, I want to mention is that all the work I'm going to present is really done by a really gifted set of co-workers that listed here. I'm very grateful to, and also we enjoy a lot of beautiful collaborations, in particular with Michael Gordetsky, John Bowers, Neil Baba, Christian Kuhs, Paul Seidler, and Tobias Hare. Okay, so maybe as a let's see if I forgot to add the wireless. Okay, let's see. That should work. Oh, okay, that works. Okay, see? Yeah. Okay, good. This works. Okay, so kind of overarching kind of motivation for the presentation I'm going to give. Let me just mention that kind of a lot of the work we're doing, and also many others in the field, is really motivated by the idea to pursue systems with very low dissipation. And it's very obvious to physicists that systems with low dissipation are really central to precision measurements. But not just that, also to technology. Okay, and the examples range from atomic force microscopy, where you make or reference cavity for lasers, where you have very large so-called optical quality factors to generate the lasers that they can interrogate kind of neutral, atom transitions for optical clocks. Timing uses quartz crystals. And there again, you use a high quality factor to have systems with high stability and high accuracy. But likewise, some of the very ubiquitous technologies that you're using today, like like cell phones, they use FBAR filters, where again, it comes down to mechanical quality factors of materials that allow you to filter, for instance, the signals that you have in your cell phones. Perhaps the most fascinating experiments of mankind in terms of precision, like the gravitational wave observation, LIGO, Virgo, and future Einstein Observatory. They use also mechanical oscillators with very large quality factors, again, with the motivation to get very low thermal noises. So the dissipation determines many things: phase noise, coherence, force noise, decoherence rate, field enhancement. And it goes without saying that one continued effort that is being made here and also elsewhere is to push the quality factors of superconducting junctions and transmods. So what I like to talk about today in particular is actually the quality factors and losses in integrated photonics, or to be more precise, using resonant devices, so-called optical microcavities. And I show a slide actually, which is very old. It dates back actually from PhD work, which is almost now 20 years actually. But it shows you that having these very large quality factors, not just purely driven with the aim of improving performance, but also there's sometimes this new physics you can discover. And I'll give two effects actually. One of them I will not talk about today, but one observation that we made was that optical resonators can both serve as an optical resonator and a mechanical resonator at the same time that are coupled by radiation pressure. So by the fact that there's raising incidence and transfer momentum. And this is now very well understood that this is an optomechanical interaction that couples the mechanical degree of freedom, AT plus B dagger, to the number of photons in the cavity, and gives rise to a whole series kind of phenomena that allows to achieve precision measurements of mechanical motion, cooling to the ground state, entanglement, and many others. I won't discuss this today, but what I would like to discuss today is another effect you can explore naturally in systems, and that is the Kerr nonlinearity. So materials like glass or dielectrics, their first correction to the nonlinearity when they have no inversion symmetry, okay, is third order. So you have a sort of four-wave mixing process. And it turns out that these optical microresonators that can finite small volume for extended amount of time give rise to the formation of coherent optical frequency combs. And as I will describe to you, actually also so-called dissipative Kerr solitons. These are short recirculating pulses. And so we've kind of a long way in this kind of research, because now a lot of the maybe early playful experiments have really ventured into a regime where the question is, can we transition this technology out of the lab and really make it a technology that has a place in the real world? And so that's actually what my talk will much be focused upon. And so I'm going to leave those kind of early experiments kind of as an example, but really focus on actually how to make nonlinear integrated photonic circuits that can address two needs. One of them is these chip-scale frequency combs. Other parts are more emerging, like cryogenic interference. I also like to mention very briefly only that some of the research I was showing also led to a spin out. So I co-founded with two of my coworkers a company called Ligent Tech. I'll tell you more about it. That is commercializing low-loss integrated photonic circuits based on silicon nitride, which is a particularly suitable material for nonlinear optics. Even though I'm focusing only today on chip-scale frequency comb, let me mention that there's also a number of emerging new applications that we're pursuing, particularly when it comes to connecting the microwave domain with the optical domain, where we look at cavity electro-optics and piezo optics, where we use low-loss integrated photonics with piezoelectrics to make converters that convert microwave to optics, which I know is also here being pursued. And the very recent direction which we embarked in with Klaus Ropers from the Max Planck in Göttingen actually is coupling free electrons to integrated photonics. We found out that integrated photonics offers actually a superb way of manipulating the electron wave function. I'll not discuss it, but I want to mention that there's a whole range of new experiments that are opening up by making use of these integrated photonic circuits. So I'm starting to, the first topic I want to discuss is really chip-scale optical frequency combs. And so what are frequency combs? I think it should be known to many of the audience here. So optical combs are a way to measure optical light frequencies, and measuring optical frequencies with hundreds of terahertz used to be a challenge that was kind of for the first time solved in '99 when Ted Henge and Jen Hall realized a so-called phase coherent link from the RF to optical. The way they accomplished this challenge of measuring the optical frequency of light, or as Ted Henge says, is the heartbeat of light, is to make use of a mode-locked laser that has a certain pulse repetition rate. So it produces regular kind of self-similar waveforms. The underlying carrier can actually still have different velocity than the pulse group velocity. And so that's why this ruler in frequency domain that is formed by the Fourier transform of the pulses doesn't start at zero, but has a little offset, so-called carrier envelope frequency. Now, I won't go into much about detail, but I want to mention that by making combs that are full octave in bandwidth, by broadening the spectrum coherently, which was a very important observation that was made by Ranka in '99 using photonic crystal fibers, you can span sufficient bandwidth to measure this carrier envelope frequency and thereby create a link that spans from the optical domain, UN, to the RF domain, UREP and FCO. And this idea of having this phase coherent link really underlies all of the uses of optical combs. And they can be used in two directions. You can use it either as an optical frequency synthesizer by taking a quartz crystal and fixing your repetition rate, fixing the carrier envelope frequency and multiplying up to the optical domain. Or you can go the other way around, take one of the most stable optical transitions, for instance, the one at NIST from Jung-Yi optical lattice class based on strontium, then take the optical transition and divide it down to the RF to generate the signal that you're using for timing. So it's really these two directions that combs are being used. Now, one of the surprising maybe aspects of optical frequency combs is that they're not just used for optical frequency division or clocks. Clocks is evidently one of the key applications, but there are many more applications where the equidistance lines that an optical comb actually provides can be useful. This can be in spectroscopy and calibration, and I'll show a few other examples actually in this presentation. So what is the state of the art in optical frequency combs? So following these fundamental discoveries by Jen Hahn and Henge, optical frequency combs also very quickly transitions out of the lab. Okay, and one company that did this actually was Manual Systems. Today there are many others like IMRA and Toptica. And but if you look still today, the fields or optical frequency combs are still a quite rare technology. So maybe there are some at Yale, I don't know. But typically, it's a very costly technology. It's not been pervasive, and there are a number of reasons. One is it's based on bulk fiber optics. Okay, so it's not necessarily something that it's quite complex technology to build up. But then also there are some salient practical points. Okay, one is that the typical line spacing that you have in a commercial femtosecond laser is in the megahertz domain, whereas most signals we treat in the electronic domain are microwaves. Okay, another part is that these techniques are not scalable. These are bulk devices. If you think about the most ubiquitous technology you use, be it Wi-Fi, be it your MEMS sensors, those are made using wafer scale processing. So that has been really lacking. And what I'm going to tell you about today is kind of the story of these so-called microcosms. That started about with a serendipitous discovery of my lab of 2007 when we were working with Henge, and which allows to make very compact optical combs. And the vision is to create basically an RF optical link that is fully kind of made using wafer scale processing on a chip and takes place in microwave repetition rate mode spacings, and is fully amenable to kind of integration. And so what's the upside potential of such an approach? Well, it can really make frequency combs ubiquitous, widely used, and also penetrate applications where not used today. And so what I want to tell you in this talk is actually twofold. One part of my talk is actually focused on the fundamentals, and one part is on the applications. And I would like to first tell you about the physics that goes into making such chip scale frequency combs. So what is the physics of making frequency combs, so-called microcombs? Well, the physics is the physics of parametric interactions. And for those who work on Johnson junctions, that's well known. You have your failure to the fourth potential. And so if you have a material like glass or silicon nitride that has a third order nonlinearity, it means that you have at high electric field strength a correction to the polarization. Okay, that's a cubic in the field. You can write down a Hamiltonian, and this is say for resonator, the so-called Kerr Hamiltonian. And G here is the single photon Kerr shift. So this tells you how much the resonance frequency of the cavity shifts, okay, due to the presence of one intercavity photon. Now these numbers, okay, in contrast to Johnson junction, in optics are very small. So here we're talking about kind of Hertz level kind of shifts. Okay, so very, very small little nonlinearities. However, if you populate the resonator with a large photon field, those can be made very large. Now, one important process that we use to generate chip scale optical frequency combs is parametric oscillations. And so if you have a series of cavity lines, okay, these are with cavity decay with kappa, and you pump one of the central lines, okay, again, there's no gain medium, it's just a pure Chi3, okay, silica resonator. So it's a very simple experiment that you can imagine. Then what you have is parametric fluorescence, so you generate spontaneously scattered sidebands. And once the scattering rate overcomes the cavity decay rate, you have parametric oscillations. Okay, and these sidebands start to coherently oscillate. They follow kind of a Charlotte-Towns Langes limit for an OPO. But the important and salient aspect about this effect is that despite the Kerr nonlinearity being small, okay, the threshold for this phenomena, unlike a conventional laser, scales quadratically with the quality factor. And that tells you that systems with low loss can dramatically reduce actually the threshold for parametric oscillations. And so in a high Q resonator, these can be as low as just a few microwatts. So basically, thousands of the power in this laser quantum. And so this process was observed in optical resonators early on. And you can see here kind of signal and idler sidebands which are generated. But the important thing is this process can cascade. Okay, and the cascading of this process actually leads to the formation of a fully coherent optical frequency comb. You can also think about this process in a different way. You can think about it as a bifurcation. Okay, so if you have a cold linear resonance, okay, and you pump photons through the cavity and change the frequency, you have a Lorentzian. Due to the presence of the Kerr nonlinearity, what will happen actually is that this intercavity field will actually start to tilt. Okay, because at high intensity you get a Kerr shift. And there is a region actually where the cavity is actually bistable. And that region of bistability, okay, you actually get, you start amplifying small fluctuations. And it's this bistability in the carry response actually drives actually this parametric process. So even though parametric processes are very well known, it was only, I said, about 20 years ago where this process was for the first time observed in optical resonators. And it can give rise to optical combs. And this is another experiment we did where you can see the pump laser, you see here equidistant set of lines plotted here in wavelength of that frequency. And to confirm indeed that the spectrum we generate here is an optical comb, what we did at the time is took a commercial femtosecond phasor frequency comb at the time from the division of 10 Henge and really verified that the distance between the comb teeth is precisely the same. And what does precise mean? Precise means in 1 part 10 to the 17. So we could really demonstrate that this process of carrier frequency comb generation does give an optical frequency comb, very much the same way that there's a mode lock laser doesn't. So this process has been observed in many platforms. So it's really proliferated. So it can be seen in many different materials. And what's been very exciting to see is that materials palette has been expanded to also encompass materials such as aluminum nitride, diamond, algas, gallium phosphide, even lithium niobate with Chi2. And in virtually all these platforms, this fundamental process of carrier frequency comb generation has been observed. Now, the process, however, is a bit more complicated. And this is one of the very beautiful physical phenomena I want to today highlight and describe to you. And that is the fact that the process is not always noiseless. So in the ideal case where you generate signal either sidebands in the cascade, we call this modulation stability. You have a fully coherent optical frequency comb. However, in systems where you cavity decay rate kappa and dispersion that needs to be anomalous GBD for carrier conformation, if that one actually is quite small compared to a line width, what happens is that the first pair of sidebands you generate are actually generated very, very far away from the pump, far meaning many free spectral ranges of the cavity. And this process, when it starts now to also encompass non-degenerate phoric mixing, starts to generate subchromes around the primary lines that bleed into each other and generates many, many optical frequencies. In fact, it's very non-intuitive. If you take a resonator with large cavity decay rate, which often is the case for microfabricated devices that suffer from scattering losses, what you will see is not just one line, okay, but you will see under the cavity Lorentzian, okay, if you do heterodyne spectroscopy, you see many, many laser frequencies. So it's a whole, if you want, a whole sea of vastly different mixing products that also take us out of our conventional kind of idea that one optical cavity mode is populated with, with one frequency. No, one optical quasi mode coupled to the reservoir is coupled to many frequencies. And this is certainly not a frequency comb. And this challenge actually persisted for about 4 or 5 years in the field. Many systems that were investigated all produced this vastly incoherent spectrum, okay, of multiple comb lines in one resonance. And how can you still make a coherent optical frequency comb of this? And it turns out that it's a beautiful principle in nature of any driven dissipative nonlinear system, and it is self-organization. It's one of the most beautiful phenomena that many of you have seen, be it cloud formation, be it pattern formation, be it seeing how waters form patterns, and also pattern formation can exist in the optical domain. And so what we observed in these resonators is that if you pump, in this case, a crystal resonator, and if you were to scan the laser, so now you think of this bifurcation shown the other way, so just flip it around, you start to see that once your cavity bifurcates, you see a very noisy spectrum. If you were to look at the output of the cavity, it would actually be a broadband frequency comb, but each comb line would be consisting of hundreds of individual lines, okay, with erratic spacing. And you see that in the beat node that is very noisy. But suddenly, actually, when you tune the cavity further, okay, you suddenly see actually that everything becomes very quiet. And you start to see discrete steps in a transmission spectrum. And so what are these discrete steps? And these discrete steps, in fact, they are transitions that the cavity is making from having n solitons to n-1 to n-2 until the different pulses have all vanished. And so what is really happening here is that this cavity, okay, which is nothing else than kind of described by the Lenzman equation, okay, so you have a drive, you have a decay term, okay, you have phoric mixing terms, and if you simulate these coupled mode equations, you can simulate, okay, the evolution of the field inside the resonator. Now this equation, written here in frequency domain, where each mu will be a different mode, can be recast also actually in a mean field approximation. Okay, in fact, it resembles the so-called nonlinear detuned dissipative Schrodinger equation. So there's now A in this case is the mean field envelope, there's a dispersion term, there's an operator associated with nonlinearity. And this right-hand side of the equation, sorry, left-hand side of the equation, this admits a solution of solitons. Okay, these are the same solitons you know from optical fiber. But the deviation in this equation is that there's a right-hand side. It has dissipation, detuning, and a drive. And so that's why the solitons we generate are not conventional solitons. They're solitons of an open system. They're solitons of a cavity-coupled environment. That's why they're called dissipative solitons. And so in some sense, they're a double balance of dispersion nonlinearity and parametric gain and loss. And they can be spontaneously generated by driving the cavity in this modulation and stable regime from which they emerge. And so what happens in the cavity, if you then simulate the phenomena, is what happens is that you start to drive the cavity, okay, up to the bifurcation. You start to first generate coherence in modulation and stability patterns that give rise then to a very chaotic regime, okay, and then finally in the regime on the right-hand side, you see stable waveforms emerge. In this case here, 5 solitons, and they can also decay that, and we now also understand how to switch them. I will not talk about that, but we can move the cavities, we can move the solitons in the cavity, we can let them switch, let them collide, to understand actually how this functions. But typically what's really interesting for us is to arrive at the regime where we generate one single soliton, one solitary pulse inside actually the cavity. Now this nonlinear distributed Schrödinger equation you can also take you can plot the 2 key parameters that you have in the experiment, the laser detuning and the power that you inject actually inside the cavity. And you can map out the different phase space. So these are the different phases that exist of light in the cavity. One is like chaotic modulation stability, so a chaotic waveform characterized also by long tails, actually the distribution of the fluctuations. Then you have a region where you form solitons, so single pulses, okay, locked to a CW background, and there's also Pareto solitons. And what's been very surprising, kind of very also gratifying in the last years is that this diagram actually is vastly more complex. It is modified by Raman, by mode crossings. And what happened in the last years is that many kind of phenomena that were observed in experiments, we had to go back to the theory and ask, okay, what term is missing in the theory to describe it? So that is actually one aspect that's been very gratifying. The other part is that we can experimentally access any part of this regime. And that's fundamentally different than in mode lock lasers. We have the normalized detuning under control, the power. So we can verify regions where there should be period doubling, regions where there should be solitons, soliton crystals, where there should be dynamic instabilities, and so forth. There's generally very, very good understanding now emerged of these different dissipative systems. Maybe also, since it's a colloquium, let me just make, again, also the connection to the kind of higher principle. So first of all, the equation we're simulating here has a name. It's called the Lugато-Lefebvre equation. It was actually published in '87 by Giotto. Again, it's this detuned driven dissipative Schrödinger equation in this normalized form here. And what this kind of equation embodies is effectively, it takes ideas from thermodynamics that Grigorov described, which is that driven systems out of equilibrium that have dissipation tend to form patterns. And this can be seen in thermodynamics, and now also it's in the light field. This equation was published in '87, but it turns out actually it's an absolute perfect experimental replica actually of the driven Kerr resonator, as we found out over the last 10 years. So what are some of the kind of properties from a purely kind of application perspective?
That's all 1D, right? In fact, the multi-mode nature matters. So
yeah.
In that sense,
It's still a very simple system right now, and I'll say something about it. It's only one-dimensional, so this is right now just a one-dimensional LE. But to me, it's still surprising of how complicated the 1D case becomes. If you now add Raman, you add complications, but really the charm begins when you start to actually add other dimensions and start to look at lattices where you get emergent nonlinear dynamics. So from an application perspective, what is interesting about these dissipative Kerr solitons is that they have high repetition rates. So now they are naturally taking place in a round trip time of the resonator. This can be as low as a few gigahertz, but also as high as a few terahertz. We have very short pulses. We can generate pulses that are as short as just 3 optical cycles. They have a smooth spectral envelope, which you can predict by this Lugато-Lefebvre equation, and also tunable pulse duration. In fact, I'll talk about this, but the pulse duration actually is just dependent on the detuning. And the laser here can be as far as 10 or 20 cavity alignments detuned from the cavity and still sustain actually soliton inside the resonator, which is not necessarily very intuitive. You also have higher order dispersion effects. So for instance, if you have not just group loss dispersion at NMLs, but also normal dispersion. Okay, for instance, due to the material properties that change, you can also promote the generation of so-called Salton range of radiation. So Salton actually exhibits a oscillatory tail, and the spectral bandwidth actually becomes broader. You can also see Saltons that are promoted by the Raman gain, or even in the normal dispersion regime, you can form so-called dark pulses or switching waves. So there's a whole host actually of dissipative coherent structures inside resonators, okay, that are coherent waveforms that are solutions, okay, of basically these partial differential equations with some basically a dispersion operator that can be normal, anomalous, or even have higher dispersion terms. So one of the things actually that's very surprising, at least to me, is that we may often think about Photonics as being this very idealized solutions that exist in these perfect optical fibers. But what about systems with real imperfections? And what's interesting, and others have noticed, is that these dissipative Kerr solitons are incredibly stable attractors. So even if you have a resonator with not perfect anomalous dispersion, but where you have the modes being disturbed here, so this is the number of modes of the resonator, these are strong mode crossings. In these mode crossings, still solitons can form. The soliton will just emit radiation, in this case, sort of dispersive waves, to balance again, or you can think about it as balancing and dispersion, nonlinearity, parametric gain and loss, and still can actually be formed. And in fact, you can go even further and ask what happens if you eliminate altogether the group loss dispersion. Can you still get solitons? And even in the zero dispersion regime, you can still find so-called dissipative coherent structures. So in some sense, the nature of these partial differential equations is that they do admit very stable attractors. The challenge is to find them experimentally. Okay, find your power detuning where these attractors exist. But if they exist, they exist virtually as to our knowledge, in very strong perturbed systems. So many effects have been observed. I don't talk about them, but over the last years, the whole community have studied actually the non-dynamical properties of these solitons. They can switch, they exhibit Raman cell frequency shift, they can be dark pulses, they give rise to crystals, solitons that are perfectly aligned actually inside the cavity. On the grid. These crystals can also exhibit defects. These crystals can be molten. They have vibrational frequencies. Solitons that exist also in counterclockwise direction. And also they give rise to new dynamics when you have mode crossings appearing. So our understanding now of the last just 5-6 years of these dissipative Kerr solitons and driven resonators has become actually very complete. And this is despite the very simplicity of the system, just 1D system. The one thing that captures our interest right now and is to ask, okay, what happens if you make the system more complex? So a lot of the studies that were carried out today are just pertaining to the single resonator case. But we know from condensed matter physics that if you go from a single particle description to a description of an ensemble, okay, that even though the microscopic equations of motion don't change, phenomena appear. And actually the same actually happens also in these nonlinear driven resonators. So what we looked at is a very simple case. Okay, you go from n to n plus 1. So let's just, instead of one resonator, look at 2 resonators. I'm not even showing you the examples of a chain. And already in the 2 resonator case, what we find is that instead of now having just one dispersion parabola, okay, we have actually an upper band and a lower band. Okay, they're split by the tunnel coupling between resonators. What we can see then is that the Fourier mixing pathways become vastly more complex. So now instead of just having intra-band Fourier mixing, where you mix between fields in the same mode family, you have intra-band, okay, between bands. And already this tiny little change, okay, changes the complete physics substantially. And I will not have much time, but I want to tell you is that the same stability chart I showed you before, that has this nice region separated between the breathing solitons, MI, and the stable soliton, becomes vastly more complex. We have suddenly soliton hopping. We have suddenly new features appearing, okay, in terms of new dispersive waves that are sometimes coherent, sometimes incoherent. And it shows that already at the 2 particle levels, okay, this nonlinear optical phenomena are emergent. What does it mean? You cannot predict by looking at the equation what phenomena you will see. And what we're looking at the moment is lattices. What happens if you have a large chain, large 2D lattice of resonators? And for instance, if you're curious, you can also add topology. You can make an SSH model, or you can make a strained graphene model in 2D. And what we found is that the nonlinear dynamics in the system is incredibly rich. It's even quite challenging to simulate. But what we find is phenomena that you don't have in a single particle case. And one of these phenomena, as I said, is Salton hopping, where the entire waveform, the entire Salton actually transfers from one resonator to the other. Okay, that's one effect. Or we have dispersive waves appearing that sometimes are coherent and incoherent, even in the regime of Saltons being fully coherent. So we have a coexistence, okay, of coherent structures and incoherent structures. So, so beyond just purely kind of the application perspective, there's a lot of interesting non-dynamics that we can study in these systems. Where admittedly we actually have challenges. It's quite challenging actually to simulate it. So it's more easy to probe experimentally than it is to numerically simulate. I want to now kind of switch from this fundamental perspective really to something that I'm actually very passionate also about in equal sense, which is what would it take actually to make the transition of these microcosms to actual technologies. And here, you know, often the history is a good predictor of the future. And I want to put 3 examples here. So put 3 examples. So MEMS research, media resistance, and silicon photonics. And so all these 3 technologies actually start in academic labs, and all 3 are today ubiquitous. So be it MEMS research, that's in cell phones, you know, accelerometers, media resistance, okay, it replaced already, but it used to be in hard disk for at least 15 years. And silicon photonics, that's actually right now what we're using, okay, by using Zoom. Any silicon data center today has optical interconnects, and they use silicon photonics for transceivers for the QFP, small pluggable form factor interconnects. And so all these research can transition within like 10, 15, 20 years into actual applications. And if you look at what all these 3 have in common that I choose here, of course, it is that they're all miniaturized. They're all made using a large scale, wafer scale manufacturing, which really is really important to drive the cost down. But more importantly, you can leverage enormous investments made in microelectronics in terms of precision, in terms of the lithography, in terms of material quality, which is equally important. And so what are the challenges for microcosms? Well, there are 2 of them. One is you need to have, first of all, not just a lab on a chip, okay, but really, or not a chip in a lab, but a lab on a chip. What I mean by this, in many cases, the experiments that are taking place on a chip, but there's more. There's also the lasers, there's the control electronics, there's maybe actuators you need. How do you integrate those? The second part is, what's the power requirements? And it may not matter for an experiment in the lab, but in fact, for an actual technology deployable, power is absolutely essential. And so you need to have, and here again, we're winding back to the overarching theme, losses, because losses really drive power consumption. And so, so I think, even though there's many materials, I think there's one material that emerged, and there's a bit of a consensus in the community now, that this is a material that is the next silicon, so to speak, in quotation marks, in the sense that it has all the right features they like to have to serve as an ideal nonlinear photonic platform. And it turns out that material is silicon nitride. It's long known in semiconductor industry. It's used as a stressor layer in transistors for creating the party strain on silicon to increase the mobility of electrons. But typically it has one challenge, because there's high stress, high deposition stress, it's quite challenging to create very thick waveguides out of it. Thick meaning here, typically wavelength scale. Why do you need wavelength scale thicknesses? Because for carrier frequency chromes, we want to operate the anomalous dispersion regime. And this anomalous dispersion regime is only the case when you have light well confined actually inside the resonator, or sorry, inside the waveguides. And this has simply to do with the fact that if you transition from the short wavelength to long wavelength in a waveguide, there's a region with positive curvature, a region with negative curvature. The one with anomalous GVD is the one here, where the light is very well confined inside the waveguide. Okay, that's where the curvature has right sign for curve chrome generation. Silicon nitride has a number of very interesting properties. Band gap of 5 electron volts, so it's actually transparent and visible. Has a refractive index of 2, sufficiently high to guide light. Okay, also and have oxide as a cladding. It's CMOS certified. In fact, it's already used in CMOS foundry. It has no 2-photon absorption in the telecom band. It has a high effective nonlinearity, about a factor of 10 higher than silica. Effective nonlinearity is 100 higher, and also it's a space compatible material. It withstands very high actually doses of neutron radiation. Now, so even though it had all these beneficial properties, it's been only in the last, say, 10 years that the research really allowed to capitalize on these properties. And one of the kind of general challenges, not just of silicon nitride, but integrated photonics is our losses. So even today, silicon transceivers that are used in data centers, they use the enormous investments made in the semiconductor industry. They still typically, in the case of SOI, have losses of tens of dB per meter. So even Global Foundries TSMC, when they make silicon photonic circuits, their losses are typically dB per centimeter, very large. If you think about optical fibers, Kao taught us, can have losses of 0.2 dB per kilometer. And so you can ask yourself the question, what makes fibers so special compared to integrated photonics? So how can you reduce the losses of integrated photonics so level, maybe not approaching the fiber, but at least come a bit closer to fibers? And so that question, why would you want to work on this? Well, it has a number of important repercussions. If you had more efficient integrated photonic circuits than silicon, you can make very efficient lasers, not just efficient, you can make them very low noise. You can also make software microcombs operate into this inverse square dependent of Q with much lower thresholds. And you could potentially also unlock other applications by down the platform with lithium niobate, for instance, as we'll describe in the last few minutes. So how do we overcome these problems of silicon nitride to make it really low loss? And that's actually a process we developed in my lab around FIFA. So the idea was to rethink the way we manufacture integrated photonic circuits. And typically the ways manufacturing proceeds is subtractively. You buy SOI wafer and you perform lithography and you etch. What our process is, it actually uses something that's very well known from this Damascus kind of ornaments or from just conventional VLSI interconnects. So what are VLSI interconnects? This is the cross section of your computer chip, AMD, ARM, or whatnot. And the key is that these interconnects are made from copper. The way they're manufactured is if you have a preform into which you put copper, and then you polish. And it's exactly the way you make these ornaments. And so we took that idea from VLSI and moved it actually to photonics and to replace copper just by dielectric. And that doesn't solve completely the problem of track propagation of silicon nitride. And that's why we added also these checkerboard patterns, which release the stress of silicon nitride. And these two things together allow you to make silicon nitride very thick, up to a micron, even more. Now you can perform even one little more trick. Okay, this preform is made from glass. And glass has a melting temperature, a glass softening point at 1200 degrees. So if you put it in a furnace and just go to a glass softening point, you can take out actually all the kind of roughness that you have in the glass. And glass is much easier to etch than silicon nitride. So in this process, okay, we can now manufacture kind of negative photonic chips that are still many orders away from optical fibers. But we're making a big step towards optical fiber. We have losses now, this shows the image here, at about 1 dB per meter. So this is an example of a 5 by 5 millimeter chip. This is a spiral here with 1 meter of length. And the loss here is about 1 dB. So these are very, very low loss compared to, say, typical kind of silicon photonic kind of integrated circuit. In terms of resonators, we can get line width of these devices of less than 10 megahertz. And not just for one individual resonance, but really across the entire waveform, across the entire kind of 100 millimeter waveform. In terms of quality factors, these are kind of 37 million Q kind of resonators that we use to test each field across the waveform. What's the fundamental limit? We can also measure that. In fact, we can look at how much heat is being generated in a sample. So how many photons are actually absorbed. We found out that the absorption limit to Q actually of this material is less than 0.5 dB per meter. So we still have at least an order of magnitude before we even hit the fundamental losses. And these losses aren't even fundamental, they're just the residual hydrogen that you can also get rid of. So there's still ample of improvements we can make. But what can we do with this 1 dB per meter loss? It's about a factor of 100 lower than silicon photonics. But we can address it to a large number of applications. I won't kind of all mention it, but I want to mention these silicon nitride integrated photonic circuits. They can serve the basis for very narrow line width lasers. They perform as good as fiber lasers and can even work as short as 460 nanometers, which is a wavelength used for strontium for the for atomic clocks. You can also use it for broadband parametric amplifiers, actually traveling wave parametric amplifiers to amplify light. You can generate solitons very, very efficiently in these. You can also low noise micro generation or endow the platform with lithium niobate or piezoelectrics with further functionality to make very efficient Voltage modulators. Over the years, we got a lot of requests from collaborators to share our silicon nitride kind of platform. And that's when two co-workers of mine, Michael Geisman and Michael Servas, we decided to start a company called Lightentech and to commercialize and democratize access to silicon nitride. And so today we are operating as a foundry. We operate out of the X Fab in Paris. So it's a big semiconductor analog mixed electronics fab on a 200 millimeter line, and producing integrated photonic circuits based on silicon nitride that can serve many applications. One thing we're particularly happy about is that we see some of it also being used by the quantum community. So this is a paper that came out actually from Xanadu, a Canadian startup. It was called Quantum Circuits with Many Photons on a Programmable Nanophotonic Chip. Actually, this chip actually was manufactured using our processes by Lightratech. It's also actually mentioned in the paper, so we don't disclose any non-public information. It's known. So it's also nice to see that also future quantum photonics will actually make use of this silicon nitride for the same reasons: low two-photon absorptions, high effective nonlinearity, very low losses. We can generate solitons in these devices of silicon nitride with very low powers, very broadband. So less than 100 milliwatt of power allows you to generate spectra that are almost 2/3 of an octave. They have smooth spectral envelopes that we can simulate with this Phase equation, take into account higher dispersion, take into account the Raman effect, and also if you want to simulate dynamic effects or thermal effects. And so it shows you with very good comprehension, at least in a simple 1D case over the resonator spectrum. Now, I will not mention it, but this silicon nitride on Lidar silicon nitride makes generating solitons sound extremely easy. Okay, you can, as I said, order the chips. You have them in a couple of months in your mailbox. You can pump them and they generate solitons. And so, together with colleagues, we've looked at many applications. Here are some that we have engaged in with collaborators. We demonstrated the solitons for massively parallel coherent communications. So where we use a soliton and use each individual carrier to encode information, send it to an optical fiber, and we could demonstrate actually that with a second soliton that serves as a local oscillator, we can perform a coherent interconnect experiment. We can also use these solitons for very fundamental experiments, something we've explored with Tobias Kipenberg. This is actually a soliton that's being produced to calibrate a astrophysical spectrometer that's used for exoplanets. The typical calibration is using argon thorium lamps, which will be faded out because they're radioactive. The frequency combs provide a much better calibration tool. But now what's important to mention is, why do you want that? Why can't you do this with conventional laser frequency comb? And the reason is that in coherent communications, channel spacing is 12.5 gigahertz or more, way too large for conventional laser frequency combs. For astrophysical spectrometer calibration, typical Shell spectrometers have a diffraction power of 10,000. To tell two comb teeth apart, the minimum spacing again needs to be tens of gigahertz. And that's actually where this microcombs really shine, is when you want to have large mode spacing. Other applications include LiDAR, more for computing, or also kits like to control. And to show one example, which again is I like a lot because sometimes again it shows how some fundamental kind of dynamical behaviors we discover lead to new unforeseen applications. Let me just mention one other example about the solitons. So I showed you this kind of simplified chart, pump power versus detuning, okay, where you have stable solitons, MI, breather solitons, and chronic regimes. What you can ask yourself is, what happens if you operate at one point stably and very quickly change the laser frequency? Naively, you would think, if you very strongly perturb the system very quickly, you should probably lose the soliton state. What happens actually is that you can modulate actually the laser frequency even very fast, even on the scale actually of it's only limited basically by the cavity decay time in the inverse cavity decay time at that speed, and still retain a soliton. And what you see in the upper graph here, it's the same soliton existing here for same different tunings. It's a little Raman offset, but it's not so important. But it shows that by very quickly translating from one spectral region to the other, we can keep the soliton. Now, what happens actually to the soliton? Well, it's a solitary pulse traveling. The underlying carrier frequency now is changing. So what it means actually is that the soliton pulse envelope stays the same, but the envelope, the carrier frequency underneath the soliton, that very quickly fluctuates. And in frequency domain, that means you're translating actually all the comb teeth. And this can also be verified in simulations. We see this. So even if you include this Raman effect, we see that the primary effect of modulating the pump frequency is only to shift the underlying carrier, not the envelope of the soliton. And now comes an application actually where this is really needed. And that application is called Fmcw Lidar. So Fmcw Lidar is a little bit tech savvy and do a little bit of reading. It's at the moment a very, very hot field. There's companies like Avon that went public at Intel. And what is Fmcw Lidar? It's a technique that measures distance, but compared to time of flight pulses, Fmcw, what it does, it measures distances by mapping distance to frequency. And it does that by taking a triangular short laser, okay, and interfering it with the reflected signal. And why Fmcw is interesting is it allows you not only to get the distance of an object, but also the velocity. So if you take the frequencies from the upward and downward ramp, subtract them and add them, you get instantaneous velocity and distance information. And this greatly simplifies classification of objects. And
That's a standard radar trick.
It's standard radar trick, exactly.
I think it's an old-fashioned radar trick.
Yeah, it's much more complex, but in optics, the control of the waveform is much more complex. And it's not much less developed than in microwave domain.
Yeah.
And so it turns out actually that our approach that actually changes the envelope frequency underneath the pulse repetition rate is a perfect way to generate actually FMC that massively parallel number of lines to perform FMCW ranging, and which is actually an outstanding challenge in the field to get video rate imaging. So we have a very, very simple way to generate hundreds of carriers perfectly chirped. So again, it's a nice example of sometimes how fundamental observations in this nonlinear driven system lead to kind of new applications. These very low losses that I described also allow us to make very compact frequency combs. These are some of the most complex ones where now the 3.5 laser is integrated. We explore here a new bit of physics where we achieve both self-injection locking. So there's a laser that's a free running line of megahertz. It's self-injection locked to one of the resonators. And then we can choose a parameter regime, which still allows us actually to generate a solitone. And this allows now to integrate pump laser, okay, and the photonic chip actually in a very compact form factor. And the electrical power we need here is less than a watt to generate these. And to show you kind of how far we've come in terms of integration, I'd like to highlight as the last example, collaboration with John Powers' group at Santa Barbara. What we took is heterogeneously integrated lasers where you have a 3.5 semiconductor die, okay, on a silicon nitride die to generate pump laser and silicon nitride comb generation on the same chip. This shows the 100-meter wafer, and so you see here in this goldish color is the 3.5, and the bluish actually is the silicon nitride. And on this one single wafer, actually, we made more than 3,000 microcombs. And so actually, it shows again this benefit of being wafer scale. And again, if you think about it, it's probably a factor of 10 more combs on one wafer than when the system is sold in 20 years. So again, shows you the power actually of microelectronic integration, where it comes to the 3.5 silicon nitride and the silicon for interlayers. Power consumption in this case is less than 60 milliwatts, so it wouldn't be without this very low loss negative photonic circuits if we could match the power levels. Because these silicon photonics kind of lasers, their powers are typically tens of milliwatt at most, and they can't be operated with high power. So again, these combs have many applications. Again, astronomy, coherent communication, distance measurement, flux, microwave photonics, synthesis, also T and dual comb spectroscopy. And the silicon nitride platform is a very good one actually to pursue, okay, in these applications. Now, in the last, say, couple of minutes, what I want to still discuss kind of briefly is also, okay, how we can endow the platform with further functionality. And this has been a collaboration with the group from Snell Barber, because in many cases, we also want to activate on laser frequency. And the way we've done this is we've used aluminum nitride and MEMS technology made for F-bar filters, and H-bar filters also used actually in group here, but raw for coupling to qubit, and integrated with integrated photonics. And by using the stress optical effect, what we can do, and playing with photonic mode engineering, we can make lasers that can be exceptionally fast tuned. Because ALN is actually has high linearity. Okay, it has a very high frequency. Typical cutoff frequencies of the H-bar mode, the F-bar mode is about a gigahertz. Low linkage current, and also it's cryogenically compatible. And above all, it's an established MEMS process. And so with Sunil Barber, we demonstrated, for instance, lasers that have flat activation response at their frequency up to 10 megahertz. So if you're a laser kind of physicist or know something about lasers, it's very rare you find bulk lasers actually that can be tuned up to 10 megahertz with a flat response. And what's equally interesting is that the phase noise of these devices combined with these low losses can be on par with that of a fiber laser. So we're now kind of in a regime, okay, where we can make integrated lasers or frequency combs that are not just compact, scalable, but also the performance metrics exceeds what can be done with bulk lasers. And I think that's actually a very important change compared to integrated photonics maybe 5 years ago. In data centers, the performance is not so important for lasers. But now with silicon nitride low loss circuits, what we see is that we can achieve the same performance as state-of-the-art fiber lasers, so fiber sensing, plus achieve record kind of tuning rates. Plus silicon nitride itself is transparent down to 4 nanometer and up to 2.6 micron. So you can make lasers for LiDAR, you can make lasers for strontium clocks, or if you want for methane sensing, all in one uniform kind of technological concept. And so, so that's why we think right now there's really a kind of a nascence of integrated photonics made possible by these new materials with these very low losses. And you can also look at applications in the domain of quantum induction. Here's an example, again, with Nobamba, where we have 2 resonators in silicon nitride. Sorry, the scale bar is missing here. This is about 30 micron. And what we're doing here is we have a very, very small H-bar cavity that couples an acoustic mode at a few gigahertz to the silicon nitride. We get a stress optical effect. We have 2 optical modes here that are split by 2.7 gigahertz. What we can do with the system is inject, okay, microwave signals, okay, into the feed line. They're coupled via the piezoelectric effect, okay, into acoustic waves, and then coupled back to the photonics. And with this system, actually, we can even operate in a regime of quite interesting high cooperativity, which is needed to get a converter that operates that can convert 1 microwave photon to 1 optical photon. Already in a low cooperativity regime, actually, it's interesting because you can use this scheme here to generate, for instance, entangled photons, microwave photons, and optical photons. And this approach here we find very interesting because it doesn't use any superconductivity. So the light actually does not interfere with any superconducting resonator. We just use the H-bar, very small mode by mechanical cavity, and then again couple the microwave mode to 2 split optical modes. And here the splitting is really key, not just in terms of frequency, but also in terms of the line width, because that determines the cooperativity. Okay, then last, just one slide I want to share is with this low-loss silicon nitride platform, you can also ask, can you add further functionality? Can you add an apocalypse effect? And one thing that we can do is we can make very low voltage modulators with this technique. Our kind of idea is to make modulators that not only use, say, a few volts switching voltage, but rather use only a few hundreds of millivolts. How would you do that? Well, one way is to make a very, very long modulator. Okay, let's say it's half a meter long. That way you can reduce the switching voltage. If you apply it to the field of cryogenic interconnects, then you know that the signals propagating down coax lines are only a few gigahertz, so still comparatively kind of slow signals in terms of frequency. So what you need is a very low voltage, low bandwidth modulator to convert these signals. And our idea is here to use an optical fiber, a very efficient modulator, to take the signals out of the fridge. Why we want to do that? Okay, because of the large discrepancy of heating. Optical fibers are perfectly transparent to optical frequencies. They're very poor thermal conductor. You have 10 microwatt of heat flux from room temperature to 4K. For coaxial cable, this would be more like a milliwatt. And so we believe that optics, perhaps, maybe not, maybe, we don't know, it's an open question. You could find a comeback, not in data centers, but now maybe cryogenic interconnects for very efficient readout of superconducting circuitry. So this is an ongoing quest we're making. We did some proof of concept experiments to show that even lithium niobate modulator bolted down to 4K can be used to read out kind of superconducting electromechanical circuits. But the real challenge is, okay, to make this readout basically add little noise. And that means what you have to do is you have to ensure that the added noise by your readout chain is lower than the readout chain, say, of a hand amplifier. What would you need? You would need a 55 centimeter kind of long modulator with, say, 10 milliwatt of optical power. This would be leading to a VPI 50 milliwatt, and that would be added noise of about 20 quantum per second per hertz. And so how to make this is of course challenging. This is not something you commercially buy, but this is our approach to it together with IBM, and we are working on bonding a thin film lithium niobate onto silicon nitride to make very low VPI modulators based on silicon nitride platform. So summarizing, I hope I've been able to share some of the enthusiasm I have for seeing that integrated nonlinear photonics is becoming really a very active field due to new materials, lower losses, and the ability now to miniaturize traditionally bulk optics elements in very compact form factor, and also explore kind of novel interaction of light and microwaves and light and mechanics. Thank you very much.
So that's questions for Tobias?
I was wondering if you could give us a sense of the optical powers that you use. So you mentioned at the beginning that the G's to kind of scale with the power that you launch in. But I kind of missed that. And sort of connected to that then is, you said sort of heating is limited by thermal absorption in a dB per meter. Do you have a sense of sort of the strength of, or the level of power that would be?
Yeah, so one of the surprising things about silicon nitride is actually that we've launched as much as 10 watt of optical power in a 1x1 microwave guide. If you do it in an optical fiber, it would never work because of Summa-Bruin scattering. You would actually get it reflected. So it turns out actually the material has a number of really interesting properties beyond just the photonics and the band gap, which is also the fact that Bruin is very weak, and also Raman is actually very weak compared to fiber. The residual absorption that we see is actually less than that. It's 0.15 dB per meter, and this actually is very likely still hydrogen in the films because the precursor are DCS and silane. And so one of the kind of future things we like to do is, for instance, look at using silicon tetrachloride as a precursor. So you remove any hydrogen from the reaction, and then you could potentially even take out the residual hydrogen that's inside the film. So in that sense, yeah, there's still a lot more room for improvement on losses. The second part of your question was?
Was really just trying to turn that into a power, the sort of 0.5 dB per meter.
Power in sense of these are just linear losses, right? And,
Yeah.
But the power, the losses in the silicon nitride are effectively power independent. We don't see any effects that are related to saturation. So opposite maybe to the microwave domain where you have such absorption, in the optical domain we see no difference in the powers. You asked also about, I think, about the G's. The G's actually say here are a few hertz. Number of photons in the cavity can be extremely high, so you can have easily 10 to the 8, 10 to the 9 photons, even more in the cavity before we get these parametric oscillations.
Just I have a question about the version. So you stress the fact that you need an open system for them to work, and that you need to have some loss. So could you maybe expand a little bit on this? Is there any requirement on the loss, whether you scattering, absorption, or any coupling to a path give you this result?
Yeah, I think on the level of the Luat-Lefebvre equation, it would simply be any type of loss you can have. So any type of loss, I mean, that would basically take your intercavity, your mean field and couple it to an environment. Of course, things can become tricky if you had a multimode system where you couple to the same path, because then you can have, of course, interferences. But on the level of this very simple kind of dissipative Carr-Saltons, any loss will do. But in some sense, the loss is natural in the systems. In optics, any cavity has a finite loss. In that sense, the loss is not something that is added to the experiment, right? It would rather be even difficult to create the lossless case, which is kind of the fiber optical case that people have been studying in the early 80s.
That's nice talk. So I'm wondering, in this LiDAR experiment you have, when you change the laser wavelengths of frequency, how fast do you do? Like, the photon lifetime is like 5 nanoseconds. Do you do within 5 nanoseconds?
So the limit, yeah. So limit in the scanning, the fastest you can tune is basically kappa and inverse kappa. And so this would be, say, for 10 megahertz cavity would be 10 to the 14 hertz per second. So this frequency we don't reach in these experiments. So what we typically have is excursion, say, of 2 gigahertz, and we do this as fast as, or basically pump lasers allow. The fastest we've tried there is about 1 megahertz. The repeated to 3 gigahertz distortion at 1 megahertz, which is still kind of, I think, tuning rates of 10 to 11 to 12 hertz per second.
Does that break down if you go slower? Is there a
No, slower would always actually. At the better would always will just. So in that sense, there's no. You can say that the sound and the pulse itself never group velocity or pulse envelope never reacts to change in the carrier. So you could change it very slowly, very fast. The only limit is what Hans said is if you scan faster than kappa and inverse kappa, which in our case would be 10 to the 14 hertz per second, then at some point you become non-adiabatic. But these are exceedingly fast scan rates. So,
but you not really look at that. If you look at the lifetime of a photon, which is tens of nanoseconds, right?
Yeah.
But if you sweep your drive from 2 to 1 faster than that, wouldn't you have adiabatic frequency change in that way? Or there's mix of colors there?
Yeah, so I agree with what you said. So initially I would also thought, but in fact, if you even if you so when you would get adiabatic effects, if this from here to here would in fact be your lifetime. So
Right.
you must lifetime the photon.
Right.
But in fact, it's even more stringent because this excursion here is not just kappa, it's actually our case many kappas. So already this little small excursion of kappa needs to be bound by inverse kappa. Right. So, but even for 10 megahertz line with resonator, which actually is exceptionally good, that limit of speed is like kappa squared, so 10 to the 14 for 10 to the 7, which is exceedingly fast. So it's much faster than what's needed in any practical FMCW application where you scan at most with a megahertz. So this was kind of also to get, yeah, one of the, say, non-intuitive aspects of the dynamics.
And actually, speaking of FMCW, can you comment? Maybe perhaps I missed how does having the comb benefit? I thought you can do FMCW with a single monochromatic field, right?
No, that's people also do. And the challenge, say, one of the challenges in the field is if you look at how time of flight works right now, say, then what is done is actually that you have multiple lasers. Actually, the state of the art, I think, from it's called Luminar. They have 128 lasers that send off pulses in parallel and get back actually the signals in order to get a the ability to get a video rate frame rate. So you like to have in principle the entire scenery with at least 80 to 100 hertz.
So you like to multiply, take each of these cone lines and each of them is a pixel in a way.
That's already done in time of flight, where you have 128 kind of channels. And typically what you do is you use basically the fast access for this. And so here you could use the same, you disperse each of the channels. And just like it's done in time of flight right now, to get basically a sparse image, say in the vertical direction, horizontal direction, then you just you apply MEMS mirror or typically Galvo to get the data scanning. Because currently used single frequency FMCW cannot get the frame rates required for video rate imaging. That's the issue because there's a certain dwell time associated with each pixel because if it's scan up and scan down, and then it's a signal of noise matter allowing it to integrate. And with a single frequency, you will not be able to do video rates. And that's why the parallelization kind of is a must, and it's unclear how industry will, what are the approaches. And so one of the ideas will be actually, again, it's early stage, but still one of the ideas will be actually use a code source to generate all the, say, 100 channels at once with one common drive electronics. And also, you don't need any guard bands because you use this commercial kind of telecom demultiplexers to pick out each channel.
So I have a question. So when I heard a talk from Carrie about this, there was a pretty long section on the fact that the comb teeth are not necessarily phase coherent, and you have to kind of do both some modification of the design and et cetera to actually get them to be phase coherent. And I didn't see that coming.
So yeah, so maybe Karen and I have different ways to explain the physics. So in the end, the physics that is precisely this one I mentioned here. So you have the forward mixing appearing.
Yes.
Then it starts to cascade. First degenerate, then non-degenerate, and then it generates this very complex kind of pattern of comb teeth. And this creates a region. I think the slide I want to show is this one actually here. Here, exactly. So this creates a region where you have spatial-temporal chaos. So what's shown here in vertical direction is phi, is the angular coordinate.
Yeah.
So what you see here is periodic waveforms, here chaotic waveforms.
Yeah.
And then it's a little transition you make to a stable solenoid. And it turns actually out, and that this was very hard to get to for very mundane but very important experimental reason, is the solenoids live in the bifurcation region where the laser actually, it turns out, is red detuned from the cavity resonance. And cavities, whenever they heat, they'll shift to actually to lower frequencies. So it turns out that sitting with the laser on the red side of the cavity resonance is unstable. You're trying to kind of, you have to lock on a cliff. The reason that turns out that actually it again becomes very simple is that if you make circuits that are very, very low loss, so I was looking at circuits and showed it, but actually it turns out if you do a response measurement, we see the carrier effect at DC. There's no thermal effect. And it turns out that the solenoid itself stabilizes the system. It's autonomously stabilized. So in these very low loss
very low absorption resonators. All you need to do is take a laser frequency and you sweep over the resonance, sit there, you generate stable solitons. It's extremely easy.
So there was nothing about using mode crossings to tune the dispersion? I thought there was some cavity engineering.
Yeah, you need to make sure that overall the cavity has anomalous group velocity dispersion.
And this you get kind of, if you work with, in the case of silicon nitride, you just get it by working with thick films. If you work with thick films, then what you have is automatically kind of dispersion.
You operate a regime kind of where the refractive index has this negative curvature here with respect to wavelength. And that gives you the anomalous QED that you need to promote bright solitons. But we understand now that you don't even need that. You can also work in a regime of close to zero dispersion where you also can generate stable waveforms. In fact, these resonators in almost any dispersion regime, they generate waveforms. The simplest and most easy, so the simplest form are these bright solitons. They are second parabolic, but then there's also more complex interlock switching waves, zero dispersion solitons. But they always are attractors that are fully coherent.
Any final question? Last question? If not, let's thank Tobias again.
Tomorrow, but I'm not here.
Oh, yeah, no, you did perfectly.